Thank you for coming. I would very happy to present a talk by Branislav Mikusik, who is a postdoc visiting at Stanford University, and Jana Kosička, our very own expert on structure from motion and stereo. And they will talk on how to do plane sweeping stereo in man-made environments.
Hi, so I'll just tag along here for first few slides, and then I'll pass the token to Branislav. So I just would like to provide a little bit of a motivation and put the work in the context of some related work which many of you are familiar with. So I hope the approach of acquiring 3D models from images is no news to this audience, and it has been sort of proven very useful in the context of many settings. There are a lot of interactive systems to do so. There are a lot of automated systems. So in this talk, we'll present an approach which tries to advance the classes of techniques which strive to do it in an automated manner. And then the setup is that given multiple views of the scene, you would like to automatically recover the 3D structure, and this is also known as multi-view stereo in computer vision community. And this is a broad class of application to general modeling, for example, historical preservation, sort of urban modeling of cities, indoors, outdoors environments. And it provides a good alternative to other sensing technologies which are commonly used in this setting. For example, laser range scanning, because first the images have a fairly good lateral resolutions. You can capture them in high resolution and high frame rate. And the sensors are relatively inexpensive, and they're easily accessible, they're passive, and they're easily transportable. So you can use this technology in the places where it might not be easy to carry the laser rangefinder. So the general ingredients, all of which will instantiate here of the multi-view stereo, is the fact that you assume that the camera poses are known. And then there's some choice of photometric consistency function, which I'll describe what it is in a second, and then the choice of representation and algorithm. So the photometric consistency function is really the crucial part of any algorithm which is using multiple views in order to reason about the 3D structure of the scene. And the basis of that function is that if you would like to reason about some point in 3D, and you would like to know whether it's photometrically consistent, if you take a rays and project those rays into the individual points in the respective views, if the projection comes from a particular point in the 3D, then some photometric properties of those projections have to be consistent, and so their respective errors should be different. And if it didn't, then there should be some differences. But already on this picture, you can easily see that, and as you will see, you can have environments where often if you have inconsistent points, if you do not have properly designed photometric consistency measures, they will appear to be sort of consistent in a sense of having very small differences. So if all the surface of this of the shape would be uniformly shaded, or it would have no texture, it would appear equally likely to come from different directions. So these are some of the issues which the algorithms need to resolve in order to achieve robust solutions in the presence of these ambiguities. So the general ingredients of any algorithm is that you assume that you have known camera poses, so we are not going to be discussing the problem of how to estimate where the cameras are, and that's a separate issue. And then once we choose the photometric consistency measure, we'll pick a particular representation. The class of problems which we'll focus on in this talk is that we'll actually assume that we'll have only a sparse set of views from which the scene is observed. And this is quite important because if you have a sparse set of views, then you can accumulate this photometric consistency measure. You have only small number of exemplars which you have in order to reason whether the things are consistent. And we'll also discuss how to deal with the regions which have low texture and repetitive structures, which are also the cases where the standard photometric consistency measures and the standard representations do not handle well. And these are all the instances which you typically encounter very frequently in indoors and outdoors environments and urban settings. So this is just a couple slides of the review of the existing work. So most of the multi-view techniques fall into this category of pixel-based, where the problem is formulated of, given each pixel in some reference view, compute the depth of each pixel by viewing them in sort of respective views. And there has been a great success achieved in this type of formulation, but most of the settings assume either highly textured objects, as sort of reflected in the standard benchmark data set of the Middlebury Stereo web page and the data set. And they typically assume that you have very large number of views and very small baseline. So, for example, the picture on the right has been reconstructed from 128 images taken from Flickr. So given that you have such a large number of views, then you can get by with weaker photo consistency measure, because basically every patch is being seen at least in sort of 50 views. So the question is, what can you do if you have small number of views? So imagine that you would like to do it only from 3, 4, 5 views, or whatever views you need in order to cover the visibility in a sense of each patch being visible at least in 3 different views. And another kind of setting which is hard to adopt in urban environments, that we often do not have control settings for acquisition of these images. And often the lighting changes dramatically, and that sort of causes the problems with the photometric consistency measure. So another sort of motivating line of work which motivated us to rethink some of the basic things are sort of recent developments in the single view modeling, where the single view modeling techniques, which came out in sort of couple of years back, assume, as opposed to trying to recover the depth per each pixel, tried to formulate the depth recovery problem at the level of superpixels. So given some region over segmentation of an image, try to either assign a depth or label to each superpixel such that some overall consistency is maintained. So the picture and the movie on the right, you see the single view reconstruction of the work of Hoem and Efros, where here the problem is formulated as an optimal labeling problem where each superpixel is assigned one particular label, where label corresponds to one of the 3 normals, so vertical, horizontal, or sort of the back plane. And so here you can sort of achieve very impressive reconstructions, but the number of labels is very limited. So you can only get hold of the very coarse structure. And then the picture on the bottom is an example of the reconstruction which was achieved by the approach proposed by Ashutosh Saxena and Andrew Ng, where here again, there is a mapping learned between an appearance of each superpixel and the depth, which then enables you to estimate the kind of posterior probability of a depth given an appearance of the superpixel. And it's probably hard to see in the movie, but you can see that it is not the case that the frontal facade of the building is actually straight, and there is this kind of curved effect which, due to the formulation, kind of smoothes out the entire reconstruction. And that's also partly due to the fact that those mappings are, in a sense, quite weak, because whatever you can measure locally in a superpixel doesn't usually convey sufficient amount of information in order to reliably estimate and propagate these constraints. So I think that's all I have to say, and I'm gonna pass the token to Branislav to see about a couple ideas how we thought of improving the current state of the art.
So thanks, Jana, for introduction. And now let me continue and let me present our approach for 3D reconstruction from a small collection of white baseline images. Especially we focus on man-made environment. And this kind of environment is usually very difficult because there is often no texture as it is depicted in the images at the bottom, or there is very repetitive structure, texture, as it is depicted in the images at the top. So that's usually the reason why the standard methods fail here. Moreover, we want to handle the strong illumination, scale, and viewpoint changes and possible occlusions. So the aim of our work is to handle all such scenarios and produce a reasonable, feasible 3D reconstruction as shown here. As Jana said, there are plenty of methods for automatic 3D reconstruction. One of them is the web application Arc3D, which utilizes the many state-of-the-art techniques in the whole chain of dense stereo reconstruction. So you just upload a couple of images or your collection, your data set, and it automatically computes a 3D model, and it returns back through, and you can upload it from their web page. It perfectly works for many scenarios and for many scenes. However, as you can see, all the scenarios have something in common, and it is that they are very well textured. And second, they usually, to obtain such results, you need to have quite dense set of data, so you need many images. However, if you feed into the system our data, our building data set, you obtain the result shown here. So this is the frontal view. So this is obtained from these 4 images on the left, and this is the top view. So you can see that the reconstruction is correct only for small subset of points, and then the rest is wrongly and incorrectly reconstructed. But note that this method does not take into account any prior information about the scene which is reconstructed. So incorporating correctly some priors about the observed scene, like piecewise planarities, you can obtain much better result. You still have some holes here, but this is just because we took only 4 images for that. And this is our top view, so you can see that all planes or all dominant planes were correctly reconstructed compared to this result. So in the next, I'm going to speak about our method. So let's now assume that we observe a rigid scene by multiple cameras, and we will assume the man-made environment, and we will assume the piecewise planarities, and assume that we have a known camera projective matrices, so we know the calibration of all the cameras, and we know the poses with respect to one reference camera. So let me first explain how standard sweeping techniques work to obtain a 3D model. So the goal is for each pixel in the reference image, find the corresponding 3D position. So what we can do, as everything is calibrated, the whole setup, we can construct a projective ray going through the origin of the camera and say, okay, now our point will be somewhere along this ray. So let's take one of these points, at the depth d and projects it into the other views. And the aim is to sweep this 3D point along this ray to obtain such projections in other views to obtain some highest confidence or the best similarity measure of all the projections with this particular pixel. However, this is very sensitive to camera poses and very sensitive to illumination changes. So therefore, usually instead of single pixel, the fixed window around the pixel is taken, and instead of sweeping the single pixel, the small planar patch is swept. But then by this thing, we introduce extra parameter, which is the normal of this small planar patch. So it is then projected quite differently compared to the reference image, something like this. If we choose another normal, then it is projected in a different way. Then usually this problem is formulated in an optimization framework where we want to optimize over all normals and over all depths and over all pixels in the reference image, and we want to get a minimum in sense of a sum of two energy functions. First energy function is responsible for the consistency of all the projections across the views, so it operates only on pixels, and the second term is just a regularization term enforcing the same 3D properties of the reconstructed pixels which are in the neighborhood in the reference image. However, this problem is intractable to do it for all normals and all depths, and therefore a lot of simplifications are taken into account to get the reasonable result and to get the tractable method for solving this problem. The first approach, so I have here three recent approaches. The first approach suggests to do this optimization problem in two stages. First, the depth is estimated, and in the second stage, the normal is estimated. In the second work, they simply say that the window around the pixel is very small, and therefore the normal is negligible, and they optimize for depth only. The third approach is the closest approach to our method. It also assumes the man-made environments, and they assume that there are only some dominant planes in the scene we aim to reconstruct. So the larger window, which I mentioned, is very beneficial. So the more robust method with respect to camera pose inaccuracies can be designed, and more robust photometric measures can be designed, like a normalized cross-correlation and all these measures on more than one pixel. However, if larger the window is, more likely it is that the planar assumption will be violated, because one important assumption here is that this small window is also planar, and it comes from a small planar patch from the scene. So for example, if a pixel comes from the projection of the 3D point, which is on the facade of the building, and it's very close to the edge, then the half of the window would not correspond to that patch on this facade. So therefore, there is a drawback between increasing the size of the window. The last thing is that the Markov random field, or the graph which is built from the pixels in the reference image, is very complex because it is built on all pixels in the image. So we were thinking how to use all the advantages of having a larger window, but somehow suppress these disadvantages. And we ended up with a solution that let's first pre-segment the image into so-called superpixels and formulate the whole problem on the superpixels. So the superpixels, as you see, they usually follow the image gradient, and they are inside somehow consistent in color. For this reason, or for this purpose, we use the minimum spanning tree-based superpixel method, and we ended up with such presegmentation image, so you can control the size of the superpixels. So we have large support area because usually you see the superpixels are quite large. And as we build our graph, as I will show later, in our Markov random field on the superpixels, then the computational complexity is much less, just by factor 1,000 or something. And we formulate the searching for maximum a posterior probability of the Markov random field as a labeling problem, as I will show later. So our goal is the same as it was before for pixel-based stereo, but here we switch to the superpixels, and we want to find depth and normal for each superpixel in our reference image. In this case, it is a second camera. So we again sweep the superpixel along the projective cone and try to project these small planar patches into the other views in such a way that we want to optimize such kind of function. I will explain it into more details later. Just for now, you see that we have more terms here compared to the function I showed at the beginning, just because superpixels allow us to define more functions, and we can gain from them much more information compared to a normal fixed window around the pixels. But still, do the optimization over all normals and over all depths is intractable, and we need to take some assumptions into account. So first of all, we restrict the number of normals. So as we operate, and we assume that we operate in man-made environments, the dominant directions can be captured via vanishing points. So first we take the reference image, we fit the lines, and group them in such a way that the lines in each group cross the one point called the vanishing point. So for this image, we have 3 vanishing points. Here is on the left, here is on the right, and one is almost at infinity. So, and from this, since we have calibrated camera, we can directly compute our normal. So, and usually there are 3 dominant orthogonal directions in the standard scenarios. The method I'm going to speak about is not restricted to the number of normals, but usually we operate only on 3, and it's a sufficient assumption, can be easily augmented by an arbitrary number of normal directions. So we restricted the number of normals here in the sweeping strategy to 3, and now we need to do something with depth. So we propose to sweep along the depth range and remember only the depth candidates and optimize this function only over the depth candidates and dominant normals instead of optimizing it over all normals and all depths. So let me now explain how we obtain the depth candidates. So again, the same image, and since we assume that the superpixels come from a projection of small planar patches, we can find easily the homography mapping the superpixel to other views, and here is the formulation of the homography. So we know calibration matrix, we know rotation, we know translation vector. What is here only unknown is normal again and the depth. So let's show it on the example. I randomly picked one depth and one of the 3 normals and 1 superpixel from the reference image here. And I computed a homography and projected the superpixel into the other views. So here, this is a projection in the second image, 3rd and 4th. Here there is no projection because it's out of field, I mean the 3D patch. here it's not projected to this view. So you see that I chose wrong depth because the projection is not at the position where it should be. So now the question is, okay, let's go to sweep along the projective cone, but how to measure that these projections are okay? So again, the same image, and now what we propose is first take all the superpixel projections and first photometrically normalize all the pixels inside the superpixels, just because you see the illumination changes across the views are quite significant. If you compare the third view and the first view, it's quite different. So, but at first, before normalization, we remember the chromacity error, which is computed over all 3 color channels. And after that, we transform all the pixels inside the particular superpixel projection in such a way that the mean in all color channels in RGB is 0 and the variance is 1. So by this, we can continue and we can start just building a simple normalized histograms. So this is the histogram in 3 color channels for all the pixels inside this superpixel. This histogram comes from all the pixels inside this projection and so on. But the histograms are computed on photometrically normalized pixels. So the next stage is, okay, we have histograms, so now we need to compare them. We need to say how this histogram is similar to one computed in the reference image and so on for the other images. So we propose to design this function as it is shown here. So the first we compute the chi-square histogram difference operator. This measure operates on 2 histograms, so you feed there 2 histograms, and as a result there is a number of similarity. Plus we have here the difference between the chromacity vectors, which I showed in the previous slide, because the chromacity error takes or stores the information about the color. So when we have these partial measurements, we want to combine them in a one composite photometric measure. So we just simply sum them. But this is done in a more clever way than it is depicted here, because we don't take all these partial distances. We do it only over some subset because we want to handle also occlusions. But I'm not going now into detail how this is done, but we actually take care of the occlusions. So here is everything again. So these superpixel projections are for the depth 5. And now let's sweep this particular superpixel and increase the depth. So you see there is some movement. Also here, there is a change in the histogram shape. So let's move again, and you see that it's somehow approaching the correct position, but still we don't have a projection here. Here in this graph, all the thin curves correspond to these partial measurements, to the similarities between particular histograms to the histogram computed over the reference superpixel, and the composite photoconsistency measure is depicted here as a black bold curve. So when we move further, you see now this projection appears here, but still is not the correct position. Let's go further. So you see now we have all the projections at the correct position where it should be, and this is also indicated by the minimum of our composite photoconsistency measure. If we overshoot this correct depth, we again have some misalignment of the projection, and also this is indicated by change in the histograms. So, and these are our depth candidates. We take n best minima as depth candidates and store them in a matrix. So then for each superpixel in the image, we have, like in our experiments, we usually take only 3 best minima. So for each superpixel, we remember the matrix T, and the matrix T has so many columns as.
So you mentioned that you do this sweep for one superpixel, right? But the visibilities along the sweep depend on whatever you do for the other superpixels, right?
Yeah.
So how do you handle that?
You mean occlusions?
Yeah, the occlusions.
This was actually. So you can have, for example, you can have a superpixel. Imagine this one here, and there is a lamp in front. And when you project the particular superpixel into other views, then there will be no correct projection because the lamp will go and will be in front of your superpixel you are interested in. So it will somehow pollute your histogram measure. So this is actually done here, that we sum the partial measurements over some set k, and the k is obtained in such a way that we have a threshold here. So if the partial distance between 2 histograms is too high, there is a threshold. We don't take this measurement into account and count only those which gives us some numbers below the threshold. So by this, you can choose only the views where the patch was not occluded. If you don't have, if in all your other views, you don't have the proper projection of your superpixel because something is in front, you cannot reconstruct it.
How can you tell if the histograms are very different because there is just some high frequency edge nearby, and there is no occlusion, but there is some, you're just misprojecting because the plane is in the wrong orientation. How can you tell that that is the case and not, occlusion?
Yeah, if you don't have a correct normal, for example, then of course.
Then if the texture has an edge, it's very sharp edge, right?
Yeah, but
you still get a very wrong histogram, right?
Yeah, but if there is an edge, the edge should be also in the reference image. Or you mean if you have a zoom, for example, and your high frequency is more stronger or something? You mean this case? Oh, okay, then.
You just hook an edge, right? And you create this other mode which doesn't appear in your. I mean, I think it's just hard to differentiate, occlusion from.
Yeah, of course.
Just sliding on the same plane,
but
hitting something else, right?
Okay, you don't know whether it is occlusion or your view is just, the very strong zoom and suddenly some strong edge appears. You just don't take it into account because your similarity in a histogram indicates you that there is either occlusion or something inconsistent, even though it is consistent. You just don't take it into account and you take the other views where there is no such problem.
But once that then sort of, make it hard to reconstruct, near boundaries, near the visual boundaries of this.
Yeah, but there is an image. Where do I have the superpixels? You see that they usually follow the strong boundaries in the image. They usually follow the gradient. So this is actually done a priori before starting. So you don't have such superpixels having a strong.
Not in the other views.
Yeah, I know what you want to say. That if I project, for example, this image to the other image where there is quite strong zoom and some edges which are not visible here because you are far away, and suddenly they started being visible, that you say that they will change your histogram. Of course, they will somehow change your histogram. The question is, as you sweep along the ray, how the other projections which are incorrect behaves. Because you search for a local minimum, maybe you still will catch the correct minimum, even though it's higher than it would be if the edge would not be there. So it's a question, but you have a smoothness term and you have the regularization terms later on to somehow cope with such kind of problems, as I will show later on. So for now, let's continue, and we can discuss it later. So as I said, for each superpixel, we have this pre-computed matrix, and we have so many we have so many columns in the matrix as there are depth candidates. So if we have 3 normals, let's say, and if we take 3 best minima along the depth, so then we will have the matrix with 9 columns. So the first number is the depth where this candidate occurred. The second number is the index for the normal where it happened, and the last number is just the height of the minimum. So since we have this matrix, let's now explain the labeling problem. So as I said at the beginning, this should be, in the most general case, this set P should be all normals and all depths for all superpixels. But we restricted it to only to optimize everything over the subset of normals and over the subset of depth, and therefore this will be the S-dimensional vector L. So the labeling problem is to assign a label to each superpixel just to pick 1 column from the matrix TS for each superpixel. So let me explain it on a toy example. So I have 3 superpixels here, and I have pre-computed 3 matrices, T1, T2, and T3, which have, let's say now, 9 columns. So we construct a graph from the superpixels, and the graph will have so many objects as there are superpixels. So we have 3 objects here. Each object represents this particular superpixel, and each superpixel can have L possible labels, and this label is actually the column in this matrix TS, so is the index of a possible depth candidate. We need to set all the numbers here and all the weights on these edges. The connectivity between the objects is set accordingly to the neighboring relation coming from the input image. So if 2 superpixels share at least 1 pixel, then they are connected in the graph, and all connections between all labels are created. And we have 2 types of functions. So these first 2 functions are responsible for the numbers in the circles here, and they say how probable is that, or how costly it is to assign a label LS to a particular superpixel S. Then we have other 2 types of energies, and they operate between 2 superpixels. So they set all the numbers connecting the labels in 2 superpixels in the superpixel S. S prime means the superpixel which is in the neighborhood, and these are the particular labels. The aim is to minimize this sum of energy functions in such a way that it will create a path in your graph, just taking or picking only 1 label per object, and the minimum should be the minimum along the edges connecting the chosen labels. For example, here it is shown in a red color, and this corresponds to a label to the vector 3, which is here L and 2. So the L has the dimension of number of superpixels. So in our case, we have usually something like 400 superpixels. So you want to estimate this vector L. This is NP-hard problem, so it's not possible to solve it globally, but they are available, the recent solvers, particularly for this kind of problem. One is by Kolmogorov and one by Werner, where you can feed all your data and get a reasonable result. So the solvers do not guarantee the global optimum, they guarantee that it is usually the optimum which is found is usually very close, or it is already the global optimum. So let's now explain all the energy terms we use here. First is a photometric term, and it simply measures how well the particular or how well are the superpixel projection across the other views. So we directly take just a third number from our stored matrices, and it is directly set as it is depicted here. So lower the minimum is, more likely it is that the superpixel will get the label L as where it happened. The second, we have a geometric term. The superpixels have a nice property that their boundaries usually are consistent with dominant directions. As it is shown here, they usually follow the image gradient, which can be utilized and can be used here. So let's assume we already have detected a vanishing point, all vanishing points in our input image. We can compute the probability of each pixel to be aligned with a particular vanishing point. This is for a first vanishing point, second, which is somewhere on the right, and this is for a vanishing point, which is above. So imagine we have a superpixel like this, and the superpixel is aligned, or the boundary of the superpixel is aligned in such a way that it is consistent with two vanishing points. This is the case which usually happens, and there are a lot of such superpixels here. So how to find out that the boundary is already aligned with two superpixels? It's easy because we just follow the boundary, the superpixel boundary, and while taking a look at our probability images, and you can compute this probability of the superpixel being aligned with two vanishing points. Then we can say, okay, if we assume we have three orthogonal directions in our scene, this is very likely that such superpixel will be perpendicular to the second normal, which we already know, and then the probability of the superpixel will be, or being aligned with the second normal will be very high, which actually motivated our geometric term. So for this particular superpixel, the term will be 0 because we want to force the solver to prefer the label corresponding to the second normal. So this is possible only because we operate on superpixels, because they usually, as I mentioned, are aligned and in such a way that the boundary respect the directions to vanishing points. The other two terms are responsible for a smoothness or for regularization. So if we have two superpixels in the image and they are in a neighborhood, we won't force them to have a same normal. So then we say to the solver, okay, if you decide to put to both of them same normal, you will not pay anything, it is for free. But if you decide to put here one normal and here another normal, you will pay for that. So then the last term, called the depth term, is the term for forcing neighboring superpixels in the image to touch in 3D.
So in this last two terms, you are not taking into account the content of the pixels, right? Shouldn't you somehow penalize more, having different normals or depths if the content is the same than if it isn't, right? So if the things have very different colors, shouldn't the weight actually be smaller,
Yeah, it is very easily to be included, yeah. But the question is whether it is really true. Because imagine you have a wall, you have a white wall, and you have a picture on the wall, a poster, which is black. So you will have two different superpixels. One is totally black inside, and one is totally white. So the difference will be dramatic, even though they belong to the same plane. So there's the question whether such kind of thing will help you. So, but here we don't use such kind of thing. So these smoothness terms are purely based on geometric use. So this is the last term. And let's say we have two superpixels. We know we have our center of projection. And now we take all the pixels which are or which lie on the common boundary. and just project them. So when we take the label belonging to the superpixel S, we can directly take a look into the matrix we have pre-computed, see what kind of normal it corresponds to, and what kind of depth it corresponds to, and reconstruct the planar page in 3D. We can do the same for the second superpixel just by taking another label assigned to this superpixel. And here, our energy term is based on the distance, and it is based on the medium distance of all relative distances of the points along the shared boundary between the superpixels. Of course, this sometimes is possible in real scenarios, that even though the superpixels are a neighborhood in your image, they can be, or they do not touch in 3D. So it's a common it happens, and therefore we have a saturation measure here. So if the error is very large, we don't penalize it, or we penalize it by constant penalty. So I explained all the terms. So after setting the graph, you can run the labeling problem, and you will get the result like this for the sequence which was shown in the beginning. So the first image corresponds to the assigned normals. So here we have only two normals because the third plane, the ground plane, is not visible here. So all the pixels or superpixels assigned to the same normal are depicted in the same color. The black color here means that the solver could not decide, because we introduced one extra label called don't know label. If the solver cannot decide, or there is no information, if there are a lot of occlusions, then simply you cannot say anything about the 3D properties of the superpixel, and you simply give this don't know label. So usually it's more safe than randomly pick one of the labels. So therefore the sky here was marked as a don't know label, because it's not possible to estimate the 3D pose. Usually in a standard dense stereo techniques, the sky is masked out manually. Here, this is the raw result from the solver. This is a depth map, so all the pixels or all the superpixels having same depth should be in the same color, or should have the same color. So it is somehow more or less consistent, but not as we would like. So we propose, okay, let's now to compute the histograms from the estimated depth. So we take all the superpixels here, we take the depth which we estimated, constructed the histograms for each normal independently. So here we have two normals, so two histograms. And you see that there are two strong peaks in each histogram, meaning that there are two dominant planes, which is actually true. So you can take this into account, use Bayesian formulation, and redesign your photoconsistency or your composite photoconsistency measure in such a way that you somehow encode the prior about the possible depth in the scene, and you can get much better results here. So here we manually also masked out the sky. So you see that all the pixels now at the same depth have approximately the same color. So let me show you some results. So this is the result for our first sequence. So we just took these 4 images and computed our model. So you see there are still some errors, but this come from either occlusions or because we don't have enough views to decide and to estimate the 3D pose. So the second example is on the sequence, which is usually used. This is a sequence from Mark Polfey's group. It contains 46 images, and it's usually used to present or to show the performance of the dense stereo algorithms. This is the result recently published, the CVPR07. So color here corresponds to the assigned normal. So all the pixels on the ground plane should be green, and all the pixels on the perpendicular plane should be either red or blue. So this is our result, which is smoother. And for our result, we used only 6 images, where they used all 46 images. So we can operate on much lower set of data. So you will see now that all the superpixels are really, or they all rely on the plane. So let's move to the next example. Sorry. So the next example is the Oxford corridor data set, and there is no dense stereo method which would show the performance on the sequence because there is no texture. So the pixel-based method simply would fail here because all the patches are in constant color, and even though the images are in grayscale and in low quality, but still we can handle it and we can construct nice 3D reconstruction with correctly estimated angles and planarities in there, so we can walk through the corridor and out of it. The last sequence is again the Oxford data set. It is Wadham College. So we reconstructed the model of the building just from 5 images, and this is the result. Here what we want to show is that we took into account only 3 dominant normals, but there is a roof which is not aligned with none of the dominant normals. So what the solver or what the method did, it assigned the roof to the closest normal. So it can be seen in the video. So you see that they perfectly lie on the plane, all the superpixels. So, and even the chimneys are correctly reconstructed. The roof is not, because we did not allow the normal, which is perpendicular to the roof. Okay, so let me conclude the work. So I presented and I wanted to show how superpixels are beneficial for 3D reconstruction of man-made environments. They offer less computational complexity, than they offer more robust photometric measures could be defined, and I showed how the piecewise planar surfaces can be favorably handled using such entities and building the whole method and whole strategy on such primitives. Thank you.
How do you automatically choose the number of normals that you need? The number n?
In all these experiments, we chose just 3, as usually there were 3 orthogonal directions. Your question is how to choose it in general. You can do it like, there are methods for computing the vanishing points. And as many vanishing points you can compute it, so many normals you can take into account. Because these dominant directions are indicated by the lines. You know, and so you can run the method and you can get 10 vanishing points, which are not orthogonal, but you can say, okay, let's now do the optimization over these normals belonging to these vanishing points. So this is one possible direction.
So actually the question is somehow related to that. So in this kind of scenes that you are targeting, there are methods such as the method of Cremonese, which you can use to get the sparse reconstruction of the scene very well, and in particular the edges, right? So shouldn't that somehow be used to constrain? If you're going as far as, let's say, taking the orientation of the edges of the superpixels into account, shouldn't you take this much more reliable, structure, which is the lines that belong to each vanishing set, as a prior constraint to your method?
Yeah, but in the Cremonese's work, you mean the work where they operate on single images, or?
For instance, yeah. For instance.
Of course, I mean, we don't claim that the energy terms we define are the best, but you can, of course, include more and more information in there without the changing of the whole framework. So you still can formulate it as a labeling problem on the depth candidates, and increasing the quality of the energy functions, the better the depth candidates will be, and then the final reconstruction can be more reliable. So of course you can put such things in there.
True, but what I mean. So I think there are, regardless of whether you use superpixels or not, there are sort of two alternatives, right? Two major sort of algorithmic ways of dealing with this. One is, I look at all possible positions and orientations and put some constraints there and try to figure out this global optimal solution.
Yeah, but
right?
Nobody can solve this problem, yeah.
And so in the end, you cannot solve, and you have to apply some heuristics anyway to the global problem, right?
Yeah, sure.
The other way of doing this is sort of as a surface evolution kind of, framework, where you start with a bounding box of your scene. If you have the method from, if you have the results of Cremonese's method, you even have like the orientations, already that you have to look, right? So you can put the bounding box according to those orientations, and then you evolve that, and you try to see if you can eliminate points from the surface, right? And you proceed, pulling the surfaces downward, because, actually the global problem, it's provably not solvable, right? There is the photo hole papers which show that, there are no such thing as a unique solution to this problem. Right, so why treat it as a global problem rather than what seems more more rigorous approach, which is the surface evolution, right? Which is I will take this superset of the scene and then I will carve out all the things that I can carve out somehow and end up at the maximum thing which I can say. Maybe there are ambiguities and I cannot resolve them, but I will give you the maximum photo hole of the scene, right?
Yeah, would be actually nice to feed the same data in such kind of approach and then maybe see which is better. And I mean, the best would be, of course, to somehow try to combine the things. This would be very challenging direction. So.
Mm-hmm. I think there's also kind of a side issue. I just want to jump in. So I guess the Cremonese methods the techniques have been developed in the context of single view modeling, and one can get a lot of mileage out of that. But when one wants to use multiple views, you have to kind of work out how to fuse things and how to figure out which things are the same, despite of all the sort of photometric issues which you encounter if you have wide baseline. And the other issue with respect to the visual hull is that this method is actually computationally fairly effective. So given the fact that you are basically running the MRF on the graph of the order of a few hundred nodes, so I don't want to sort of advocate the implementation in hardware, but this is something which can actually run in real time. So there is some appeal to it from...
But that's related to the superpixels.
Right.
Not, I mean, you can do superpixels and, surface evolution, right? Or you can do superpixels and MRFs or
any combination of these things is possible, right?
Yeah.
What I'm saying is I see the strength of this more on the the superpixels than
on the MRF. So why not try? I mean, it might be an interesting idea to try superpixels and surface evolution, right? Just intuitively, it seems to me that's the first thing I would try.
It's possible. improvement or direction to go. Yeah.
In your error term, do you have any understanding on how much each of those individual terms actually contributes? And the reason I'm asking is because you chose the superpixels, and it's somewhat related to what he was saying, exactly so that they have no texture, and you can't really calculate tomographies with them.
Actually, for example, here it's not true because all the superpixels contain a texture inside.
Yeah,
and this texture is taken into account in the first two energy functions, in this photoconsistency and only in the photoconsistency.
Yes, so the early example where you had the facade, you actually put the superpixels right at all the edges of where texture had changes, because you said you did the gradient.
You missed...
Yeah, exactly this one. So wouldn't you have ruled out all the relevant parts now to give you contribution for that first error term?
There is one thing, because for some superpixels, like the superpixels here in the sky, you cannot simply say anything, because as you follow the boundary, you cannot say to which vanishing point it belongs. Then, in such a case, for example, then this term will be set somewhere in the middle, like you don't penalize this label because you don't know. And you are actually asking, here it is, sorry. So you want to know what are actually these weights.
Yes, and especially the first one.
Yeah, the first one. Actually, this first term is the most important term, because it captures the texture which is inside the superpixels, and this term is responsible for the measuring of the similarity across the views. So the rest is actually, these two are for regularization, just to have, the piecewise smooth surface or piecewise planar, and this is actually responsible just for helping the solver. But I cannot say, you want to hear which terms are the most important or how important which term is?
Well, I'm trying to understand why the first one can remain the most important if you've chosen your superpixels such that they don't have any changes in themselves, that they're basically very consistent across.
Because they still have the boundary, even though inside is nothing. Imagine you have a white wall, and then you have somewhere a superpixel which is in the middle, and the boundary is more or less random. But the superpixel, let's say, touches the boundary of the wall. So at least there is a part of the boundary which is somehow kind of right angle, and the rest is random. So this helps you a lot, because when you sweep the whole shape. And in the other views, you simply go, along the epipolar line, and you usually get the optimum, exactly the place where this perpendicular edge is in the other views. So it is indirectly also encoded in the shape of the superpixel, not only what is in the middle.
Can I ask a related question? So here you compare your approach against a purely pixel-based approach, right? And there is this intermediate creation, which is, you use superpixels for two things. One is to group pixels into regions, and two, to compute features on the regions, right? But in between, you can group pixels into regions, but then for each region, for each pixel in the region, you can just compute pixel-based measures, right? And sum all those measures as the region score. So then you still have the old features, but you have superpixels, and that's in between, and that gives you an idea of how much do you actually gain by this extra measures.
But the one thing is, you said that you can compute your similarity measure on pixels, on individual pixel,
that belong
and then
to the superpixel.
Yeah, but this is the key point, because what kind of measure you would use? You would compare,
Let's say normalized cross correlation, right?
Yeah, but for that you need a window.
Yeah,
so you need to go around.
You will go outside, so it will hurt. It's not supposed to address all the issues that you address with the superpixel, but it's a nice comparison to show how much all these extra respective boundaries during your feature design helps, right? That's all.
Yeah, but
versus grouping, which is the other kind of orthogonal axis of what you do. So I just try to break it into pieces, see how much each matters.
Yeah, but
that's all.
Yeah, okay. The only drawback I see is this computation of your photo consistency error just for a single pixel and this cross correlation, because you need a window, you need to increase the window to get much better result, more robust to illumination changes. But as far as you increase the window, you may get into problems and so on.
So what happens when a large fractions of the superpixels have boundaries that are not aligned with the vanishing points of the building or the scene, whatever?
You mean, for example, like the superpixels like this one?
Yeah, I mean...
Because here the planar assumption is also violated because the gradient here was very weak.
Oh, no, actually, I mean, you can have walls of buildings that are very planar, but any sensible segmentation algorithms will give you patches that are not a brickwork, right? Because there might be stone walls, for example. So what happens in this case?
What happened in which case, actually?
I mean, so what happens when the majority of superpixels do not have boundaries that are aligned with the vanishing points?
It does not matter, because the measure, this geometric term, which I explained, measuring the boundaries of the superpixels, it helps you only in the cases where it is possible, where you follow the boundary and you simply find out that, okay, there is no direction consistent with any vanishing point. So you cannot say anything, and then you put this term as kind of constant number, or there is some number saying that I don't know, I would rather not decrease the cost. Where you can do it, where the superpixels are aligned, then the term would go to 0. So it would go to 0 only for those superpixels where you can say something about it.